Before we begin tonight's quiet journey into the earliest chapter of the cosmos, if these slow explorations help you relax, you can gently support the channel by leaving a like or subscribing for more calm documentaries like this one. It truly helps this peaceful space continue to grow. And now, there is nothing else you need to do. Let your breathing slow. Let your thoughts soften. And drift with me into a universe before light filled the sky. Long before spiral galaxies rotated across space. Before clusters of stars gathered in brilliant cosmic cities. Before planets formed, or black holes anchored galactic cores. There was darkness. A deeper darkness than the one we see between the stars tonight. This was the cosmic dark ages. To understand this era, we must begin shortly after the Big Bang. The universe was once incredibly hot and dense. In its earliest moments, it was filled with a glowing plasma of particles and radiation, opaque and turbulent. But as space expanded, it cooled. About 380,000 years after the beginning, the temperature dropped enough for protons and electrons to combine into neutral hydrogen atoms. When this happened, light was finally able to travel freely. That first ancient glow still surrounds us today as the cosmic microwave background. And then, the light faded. Not because it disappeared, but because the universe entered a period when no new light had yet formed. There were no stars, no galaxies, no shining objects of any kind. Only vast clouds of hydrogen and helium drifting slowly through expanding space. Imagine an entire universe filled with darkness and faint gas, stretching endlessly in every direction. This darkness lasted for millions of years. Gravity was already at work. Tiny density fluctuations, extremely small differences in matter distribution left over from the earliest moments, began slowly growing. Where matter was slightly denser, gravity pulled in more matter. Where matter was less dense, space became emptier. The process was incredibly slow. There were no explosions. No bright events. Only subtle gravitational accumulation across enormous stretches of time. These density fluctuations were seeded by dark matter. Dark matter did not interact with radiation in the early universe. While ordinary matter was influenced by photon pressure, dark matter began clumping first. It formed the initial gravitational wells. Invisible scaffolding. Gradually, hydrogen and helium gas began falling into these dark matter halos. As gas accumulated, it compressed. As it compressed, it heated. But at first, cooling mechanisms were limited. The gas consisted almost entirely of hydrogen and helium. There were no heavy elements, no carbon, no oxygen, no iron. Those elements did not yet exist. Without heavier elements to help radiate energy efficiently, gas clouds had difficulty fragmenting into smaller pieces. The first stars would be different from the stars we see today. They would be massive. Extremely massive. During the cosmic dark ages, the universe was quiet but not empty. Vast regions existed where gravity was slowly pulling gas inward. Over time, certain regions reached critical density. Hydrogen gas collapsed further and further under its own weight. As compression increased, temperatures rose dramatically. Eventually, deep within one of these collapsing clouds, the temperature became high enough to ignite nuclear fusion. And in that moment, the first star was born. This happened roughly 100 to 200 million years after the Big Bang. It is difficult to imagine such a time scale. The universe today is 13.8 billion years old. Yet the first light of stars emerged when the universe was less than 1% of its current age. These first stars are known as population 3 stars. They were unlike any stars that exist today. Because the gas from which they formed contained no heavy elements, the cooling process differed. Simulations suggest they may have been hundreds of times more massive than our Sun. Some estimates suggest masses up to several hundred solar masses. Massive stars burn hotter and brighter. They live shorter lives. The first stars likely shone intensely in ultraviolet light. Their radiation began transforming the surrounding hydrogen gas. This marked the beginning of the epoch of reionization. Before the first stars, hydrogen in the universe was neutral. When ultraviolet light from the first stars spread outward, it ionized surrounding hydrogen atoms, stripping electrons from protons. This created expanding bubbles of ionized gas around each star. Gradually, as more stars formed, these ionized regions grew and merged. The universe slowly transitioned from darkness to a faint cosmic glow. But the process was gradual. The early universe was not suddenly illuminated. It brightened slowly, unevenly, in patches. Imagine darkness pierced by distant points of light, isolated stars igniting within massive halos of gas. Between them lay vast regions still untouched by radiation. The first stars were likely enormous and short-lived. Because of their mass, they burned through their nuclear fuel rapidly, perhaps in only a few million years. In cosmic terms, that is a brief flicker. When these massive stars reached the end of their lives, they exploded as supernovae. These explosions were unlike most supernovae seen today. Some may have been pair instability supernovae, violent detonations that completely destroyed the star, leaving no remnant behind. In these explosions, the first heavy elements were forged: carbon, oxygen, nitrogen, iron. These elements were scattered into surrounding space, enriching the gas. For the first time, the universe contained the building blocks necessary for more complex chemistry. Without these first stars, there would be no heavy elements. Without heavy elements, there would be no rocky planets. No water. No life as we know it. The silent darkness of the early cosmos gave birth to everything familiar. After the first stars exploded, the enriched gas began cooling more efficiently. Heavier elements allowed gas clouds to fragment into smaller pieces. This led to the formation of later generations of stars, smaller, longer-lived stars. Some of these early enriched stars may still exist today in ancient regions of galaxies. They are relics of the early universe. Meanwhile, dark matter halos continued merging and growing. Small halos combined into larger ones. Gas accumulated in deeper gravitational wells. Over time, groups of stars began forming together inside these halos. These were the earliest proto-galaxies. Not yet fully developed spirals or ellipticals, but clusters of stars embedded in dark matter halos. The cosmic dark ages gradually ended as more stars formed. Ultraviolet radiation increased. Neutral hydrogen became ionized across larger regions. The universe transitioned into a transparent, structured era. Yet even as light increased, darkness still dominated the vast spaces between structures. The cosmic web, shaped by dark matter, guided where galaxies would assemble. Filaments stretched across space, connecting growing halos. The first galaxies were small and irregular compared to modern ones. They merged over time, building larger structures. Gravity remained the sculptor. Radiation the illuminator. Time the patient witness. The early universe was not chaotic in the way we imagine explosions and turbulence. It was governed by consistent physical laws. Expansion continued steadily. Gravity accumulated slowly. Fusion ignited predictably under pressure. Structure emerged from fluctuation. Even in darkness, order existed. And the darkness itself was not empty. It was filled with hydrogen gas stretching across billions of light years. Dense regions grew slowly. Voids expanded. Filaments strengthened. The first stars did not light a uniform sky. They appeared in isolated pockets. Between them lay enormous distances. It would take hundreds of millions of years before galaxies became common. During this era, black holes may also have formed from the collapse of massive first stars. Some of these black holes may have grown rapidly, eventually becoming the seeds of supermassive black holes found in galactic centers today. Even in the earliest chapters, gravity was preparing long-term structure. As the universe continued expanding, regions far apart became increasingly separated. But within bound regions, structure became more complex. The interplay between expansion and gravity shaped everything. Dark matter halos gathered mass. Gas cooled. Stars ignited. Elements formed. Galaxies assembled. All beginning in silence. All beginning in darkness. The first stars changed the chemistry of the universe permanently. Before them, only hydrogen and helium existed. After them, heavy elements circulated through space. Subsequent generations of stars incorporated those elements. Planets eventually formed around later stars. Rocky worlds became possible only after this initial enrichment. When we look at our own Sun, formed billions of years later, it contains heavy elements forged in ancient stars long before the solar system existed. We are, in a literal sense, made from the remnants of those first explosions. Carbon in your body. Iron in your blood. Oxygen you breathe. All trace their origins to early generations of stars. And those stars trace their origins to dark matter halos forming in the cosmic dark. The silence of the early universe was not emptiness. It was preparation. A long quiet accumulation before ignition. Gravity works without noise. Fusion ignites without announcement in the void. Light spreads quietly through expanding space. The first stars shone fiercely, but there were few of them at first. Gradually, star formation increased as gas became enriched and cooling improved. The cosmic landscape shifted from darkness dotted by rare lights to a universe where small galaxies began assembling. Over hundreds of millions of years, the epoch of ionization completed. Neutral hydrogen became mostly ionized across intergalactic space. The universe entered a new era, one where galaxies dominated structure. But the memory of darkness remained written in background radiation. Even today, astronomers search for faint signals from that ancient era. Using radio telescopes, they attempt to detect subtle fluctuations from neutral hydrogen during the cosmic dark ages. These measurements are extremely challenging. But they offer insight into the first structures ever formed. Because the first stars are too distant and faint to observe directly in most cases, scientists rely on simulations and indirect signals. Computational models recreate conditions shortly after the Big Bang. They track dark matter clustering. They simulate gas collapse. They predict mass ranges for early stars. Everything suggests that the first luminous objects were rare, massive, and short-lived. They existed briefly in an overwhelmingly dark cosmos. And yet, their influence was permanent. They transformed chemistry. They triggered ionization. They seeded future galaxies. They ended the cosmic dark ages. When we observe the universe today, we see billions of galaxies. Yet all of them trace back to that quiet era when gravity was gathering the first halos. Before light filled space. Before spiral arms rotated. Before planetary systems emerged. There was darkness, structured and patient. And within that darkness, tiny fluctuations grew into the cosmic architecture we see today. The silent age was not empty. It was foundational. The first stars were not ordinary stars. They were the universe learning to shine. They were the first break in uniform darkness. And though they lived briefly, their legacy persists everywhere. In the galaxies. In the elements. In us. As we end this first part of our journey into the earliest cosmic era, imagine that deep, ancient darkness stretching across space. Hydrogen clouds drifting slowly. Dark matter halos gathering mass invisibly. And somewhere within that stillness, the first point of light igniting. A universe beginning to glow. Quietly. Gradually. Patiently. And from that first light, everything else would follow. For tens of millions of years before the first star ignited, the universe existed in near perfect darkness. There were no sharp edges, no defined structures, only faint density variations gradually amplifying under gravity's steady influence. Hydrogen atoms drifted through expanding space, occasionally colliding, occasionally clustering slightly more in some regions than others. Because the universe was still relatively simple in composition, structure formation depended heavily on dark matter. These invisible halos grew first. They formed gravitational wells that ordinary gas slowly fell into. But early gas clouds faced a unique challenge. Cooling is essential for collapse. When gas falls inward under gravity, it heats up. If it cannot radiate that heat away, internal pressure resists further collapse. In the early universe, cooling mechanisms were limited. There were no metals, no carbon, oxygen, or silicon, to radiate energy efficiently. Instead, cooling relied primarily on molecular hydrogen. Molecular hydrogen is not particularly efficient at dissipating heat compared to heavier elements. As a result, the gas clouds that eventually formed the first stars remained relatively massive before they could fragment. This is one reason astronomers believe the first stars were enormous. Some models estimate masses between 30 and 300 times the mass of the Sun, with certain rare cases possibly reaching even higher. Massive stars shine intensely. Their surface temperatures can exceed tens of thousands of degrees. They emit strong ultraviolet radiation. But massive stars also live short lives. While our Sun will shine steadily for around 10 billion years, a star 100 times more massive might live only a few million years. The first stars likely burned extremely hot and died quickly. Their deaths were transformative. Some population 3 stars may have collapsed directly into black holes without exploding. Others may have ended in violent supernovae that completely disrupted the star, releasing enormous energy into surrounding space. These explosions scattered the first heavy elements into the interstellar medium. And once heavy elements existed, everything changed. Gas clouds enriched by metals cooled more efficiently. They fragmented into smaller clumps. This allowed the formation of lower mass stars. Lower mass stars live longer. They shine less intensely. They can persist for billions of years. Thus began the transition from the era of massive primordial stars to the formation of more stable stellar populations. During this transition, proto-galaxies began assembling more rapidly. Dark matter halos continued merging, forming deeper gravitational wells. Gas collected at the centers of these halos, forming dense regions where stars formed in clusters rather than isolation. The first galaxies were faint and irregular. They did not yet resemble the majestic spirals or massive ellipticals we observe today. Instead, they were compact collections of stars embedded in dark matter halos, glowing faintly in ultraviolet light. Over time, these proto-galaxies merged with one another. Collisions were common in the early universe because structures were closer together. Mergers built larger galaxies. The cosmic web grew more pronounced. Filaments funneled gas into halos. Nodes grew heavier. Structure became hierarchical, small units combining into larger ones. All of this unfolded gradually. There was no single moment when the universe transformed from dark to bright. Instead, bubbles of ionization expanded around early stars and galaxies, overlapping slowly. The epoch of reionization lasted hundreds of millions of years. Eventually, intergalactic hydrogen became largely ionized. The universe transitioned from opaque darkness to a more transparent, structured state. Yet even after reionization, vast regions between galaxies remained dark. Space is still mostly empty. The difference was that luminous structures now punctuated the void. Looking back today, telescopes such as the James Webb Space Telescope attempt to observe galaxies from less than 1 billion years after the Big Bang. These observations help astronomers infer the properties of the earliest galaxies. They confirm that structure emerged relatively quickly on cosmic scales. Even though the cosmic dark ages lasted millions of years, they were brief compared to the full age of the universe. The darkness was temporary. The architecture was permanent. The first stars acted as cosmic catalysts. They ignited nuclear fusion where none had existed before. They synthesized elements. They ended the initial darkness. But they did not eliminate darkness entirely. Darkness remains the dominant background of the cosmos. Even now, if you look into the sky far from city lights, most of what you see is darkness punctuated by stars. The early universe magnified that ratio dramatically. Almost everything was dark. Almost nothing glowed. And within that overwhelming silence, gravity worked patiently. There is something deeply calming about this image. No rushing. No dramatic events visible to observers, because observers did not yet exist. Only hydrogen clouds drifting. Only dark matter shaping. Only expansion stretching space gently outward. The universe did not hurry toward complexity. It accumulated it. Slowly. Predictably. The formation of the first stars represents the threshold between uniformity and structured brilliance. It was the first time gravity overcame internal gas pressure sufficiently to ignite sustained nuclear fusion. It was the first time light began to re-emerge as a structural force in cosmic evolution. After the first stars enriched the universe with metals, star formation became more efficient. Galaxies grew brighter. New generations of stars lived longer. Planet formation became possible. But all of it depended on that silent foundational era. Without the Dark Ages, there would be no scaffolding. Without the first stars, there would be no chemistry beyond hydrogen and helium. Without that chemistry, no rocky worlds. No oceans. No atmospheres. No living organisms. The earliest era was quiet, but decisive. Even now, the faint signatures of that time remain embedded in cosmic microwave background fluctuations. Tiny variations in temperature correspond to the density fluctuations that later became galaxies. The seeds of stars were present before stars existed. They were encoded in subtle patterns imprinted shortly after the Big Bang. Dark matter amplified those fluctuations. Gravity nurtured them. Time matured them. And from them emerged the first luminous objects. As we bring this extended journey through the cosmic dark ages toward its conclusion, imagine once more that early universe. Endless hydrogen mist. Invisible dark matter halos forming faint gravitational valleys. Gradual accumulation. Gradual compression. And then, in one region, a spark. Fusion ignites. Light radiates into surrounding darkness. The first star shines alone against an empty cosmic horizon. Not in a crowded galaxy. Not among thousands of neighbors. But isolated in a vast sea of blackness. Its light begins changing the universe around it. Slowly ionizing hydrogen. Slowly altering chemistry. Slowly seeding complexity. It burns fiercely. Briefly. Then ends in an explosion that spreads heavy elements into space. From that explosion, future stars form. From those stars, galaxies grow. From those galaxies, planetary systems emerge. From one of those systems, life eventually develops. All tracing back to that silent age. Darkness was not absence. It was potential. It was waiting. It was the quiet canvas upon which light would eventually paint structure. The first stars were the universe's first candles. And though they flickered only briefly in cosmic terms, their influence echoes across billions of years. The cosmic dark ages were not empty. They were formative. And in their stillness, the foundations of everything we know were set. Gravity does not require spectacle. Time does not require urgency. The universe built itself patiently. From darkness to light. From uniform gas to stars. From silence to structure. And tonight, as you rest beneath a sky filled with countless distant suns, remember that everything began in stillness. In deep cosmic night. Where gravity gathered quietly. Where matter drifted softly. And where, after millions of years of silence, the first light appeared. Before we continue our quiet journey into the young universe, if these slow explorations help you relax, you can gently support the channel by leaving a like or subscribing for more calm documentaries. It truly helps this peaceful space continue to grow. And now, settle in again, let your breathing slow, and drift forward in time to the era when the first galaxies began to assemble. When the first stars ignited, they did not form within organized galaxies as we imagine them today. There were no grand spiral arms yet. No massive elliptical structures. Only dark matter halos filled with cooling gas and scattered clusters of massive stars. But gravity does not stop with a single star. It continues gathering. It continues merging. Small halos collide with one another. Gas flows along filaments. Mass accumulates in deeper gravitational wells. Over time, the earliest star clusters merged into larger groupings. These were the first proto-galaxies. They were compact, irregular, and much smaller than modern galaxies. Some may have been only a few thousand light-years across. Yet even in their simplicity, they marked a turning point. For the first time, light was not isolated. Stars formed in groups. Radiation began shaping intergalactic space more widely. Within these proto-galaxies, supernova explosions enriched gas with heavier elements. Each explosion increased the metal content of the surrounding medium. With each generation, star formation became slightly more efficient. Gradually, stars with lower masses became more common. Long-lived stars appeared. Structure deepened. Meanwhile, something else was forming. When the most massive first-generation stars reached the end of their lives, not all of them exploded completely. Some collapsed directly into black holes. These early black holes were much smaller than the supermassive ones we see today, but they served as seeds. Inside dense proto-galactic environments, black holes could begin accreting surrounding gas. As gas fell inward, it heated and emitted radiation. In certain cases, accreting black holes shone as early quasars, incredibly luminous sources powered not by fusion, but by gravity. The existence of extremely massive black holes less than 1 billion years after the Big Bang remains one of the great puzzles of cosmology. How did they grow so quickly? One possibility is that some black holes formed from direct collapse of enormous gas clouds, bypassing normal star formation entirely. Another possibility is rapid growth through frequent mergers in the dense early universe. Whatever the mechanism, black holes became part of galactic centers very early in cosmic history. Galaxies and black holes began evolving together. Dark matter halos provided gravitational scaffolding. Gas cooled and formed stars. Stars died and enriched the environment. Black holes grew within deepening potential wells. Over hundreds of millions of years, the universe grew more structured. Filaments connected growing galaxies. Clusters began forming at nodes where filaments intersected. The cosmic web, shaped initially by dark matter, now glowed faintly with early starlight. Yet even as galaxies emerged, vast regions of space remained dark. Voids stretched between filaments. Expansion continued steadily. Dark energy had not yet come to dominate, but space was always expanding. Inside bound regions, gravity overcame expansion. Between them, distances increased. In this balance between gravity and expansion, cosmic architecture matured. As proto-galaxies merged, they formed larger systems. Repeated mergers stirred gas, triggered new star formation, and built mass hierarchically. This hierarchical growth continues even today. But in the early universe, it happened more frequently and more rapidly. The first galaxies were chaotic. Star formation rates were high. Supernova explosions were frequent. Radiation fields were intense. Yet through all this activity, the broader universe remained calm and vast. Even in active regions, the scale was immense. Events unfolded over millions of years. Nothing was sudden on cosmic timescales. Over time, galaxies began to develop more defined shapes. Disks formed where angular momentum organized matter into rotation. Spiral structure would come later. But rotation already played a key role in shaping mass distribution. Angular momentum, inherited from tiny fluctuations in the early universe, guided how matter collapsed. Not all gas fell straight inward. Some of it swirled. This swirling motion flattened into rotating disks. Within those disks, stars formed along denser regions. In central regions, black holes continued growing quietly. Accretion disks glowed faintly. Radiation influenced surrounding gas dynamics. Feedback from black holes began regulating star formation. Even this early, galaxies were systems in balance. Too much star formation could expel gas through supernova winds. Too much black hole accretion could heat gas and prevent collapse. Self-regulation emerged naturally from physical processes. The universe does not require fine-tuning from outside forces. Its laws allow complexity to arise spontaneously from initial conditions. By 1 billion years after the Big Bang, recognizable galaxies existed. Some were already surprisingly massive. Clusters of galaxies formed in denser regions of the cosmic web. The darkness of the earlier era had transformed into structured light. Yet darkness remained dominant overall. The majority of space was still empty void. The difference was that luminous nodes now existed within it. The age of the first stars had transitioned into the age of galaxies. Heavy elements continued accumulating. Subsequent generations of stars formed planetary systems. Chemical diversity increased. Over billions of years, galactic ecosystems matured. The Milky Way itself began assembling through mergers of smaller proto-galaxies. Our galaxy's oldest stars date back to those early eras. They carry chemical signatures of the first generations of stars. In their composition, we see traces of primordial explosions. Carbon, oxygen, magnesium, forged in ancient stellar cores. The first black holes also continued merging. As galaxies merged, their central black holes drifted toward one another, eventually coalescing. These mergers released gravitational waves, ripples in spacetime itself. In the modern era, we have detected such waves. But in the early universe, they occurred frequently and silently. Structure built upon structure. Gravity sculpted matter across scales. Expansion continued outward. Dark matter halos deepened. Star formation lit up the web. And all of this traced back to that earlier silence. The cosmic dark ages were not simply a waiting period. They were the incubation phase of structure. Density fluctuations matured during that time. The first stars ignited because gravity had patiently built sufficient conditions. When we look at the deep universe with modern telescopes, we see galaxies billions of light-years away. We are looking back in time. Each distant galaxy reveals a stage in cosmic development. The farther we look, the closer we approach that era when the first stars and galaxies emerged. In some observations, we see galaxies forming less than 500 million years after the Big Bang. Their light traveled across nearly all of cosmic history to reach us. It is humbling to realize that even those ancient galaxies were built upon earlier silence. Before their glow, darkness dominated. Before their rotation, gas drifted slowly. Before their supernovae, hydrogen floated nearly uniform across space. Everything we observe emerged from gradual amplification of tiny early fluctuations. From small differences grew enormous structures. From faint gravitational wells grew galaxies containing billions of stars. From isolated proto-galaxies grew clusters spanning millions of light-years. And from those clusters emerged environments where planetary systems could form. Even our own solar system, forming 4.6 billion years ago, is a descendant of that first luminous era. The oxygen we breathe, the iron in Earth's core, the silicon in rocks, all were forged in stars that existed because of dark matter halos forming in early darkness. The birth of galaxies represents the universe achieving organized complexity. The birth of black holes represents gravity reaching deeper extremes. The interplay between stars, galaxies, and black holes defines cosmic evolution. Yet beneath all of it, the underlying framework remains dark matter and expanding spacetime. In the vast timeline of the universe, the transition from darkness to galaxies happened relatively quickly. In less than a billion years, structure became widespread. But compared to a human lifespan, even that period is unimaginable. Millions of years pass silently in cosmic terms. Galaxies evolve slowly. Black holes grow steadily. Star formation fluctuates over eons. Nothing hurries. Nothing rushes toward its final state. The universe unfolds through accumulation and transformation. From darkness to first light. From first light to galaxies. From galaxies to clusters. From clusters to complex cosmic web. As we conclude this second part of our journey, imagine the early cosmos once more. Dark matter filaments stretching invisibly. Proto-galaxies forming at intersections. Massive early stars igniting and exploding. Black holes seeding galactic centers. Light spreading gradually across expanding space. What began as darkness became architecture. What began as uniform gas became luminous systems. And all of it emerged through quiet gravity and steady expansion. There was no grand switch flipped. No sudden illumination of the entire sky. Only gradual emergence. Bubble by bubble. Halo by halo. Galaxy by galaxy. The first stars ended the silent age. The first galaxies transformed the cosmic landscape. And from their formation, every later chapter of cosmic history followed. Even tonight, as you look up into the sky and see distant points of light, you are witnessing the result of that ancient transition. A universe that once lay in complete darkness now shines with billions of galaxies. Yet darkness still fills the vast majority of space. And within that darkness, gravity continues shaping structure gently. The silent age gave birth to everything. From hydrogen clouds to galaxies. From massive stars to black holes. From darkness to complexity. All unfolding slowly. Calmly. Inevitably. And beneath it all, the same quiet physical laws continue guiding motion across deep time. The universe began in brilliance, entered darkness, and emerged into structured light. And the echoes of that silent beginning still resonate in every star that shines, including our own. As galaxies continued merging in the early universe, structure became increasingly complex. Smaller systems were absorbed into larger ones. Gas clouds collided and compressed. Star formation surged in bursts triggered by gravitational interactions. These early mergers were not orderly or graceful. They were turbulent in structure, but slow in timeline. Millions of years passed during each interaction. From a human perspective, they would appear almost frozen in motion. During these mergers, angular momentum played a decisive role. When gas clouds collided, they did not simply fall straight inward. Instead, their motion caused them to rotate, flattening into disks over time. It is through this process that many galaxies eventually developed rotating structures. The earliest disks were irregular and chaotic, but gradual settling allowed more stable rotation patterns to emerge. Within these rotating disks, spiral density waves could later organize stars into arms. Spiral arms are not fixed structures. They are regions where density increases slightly, triggering star formation as gas compresses. Even this elegant design traces back to early fluctuations amplified by gravity. Meanwhile, at the centers of these growing galaxies, black holes continued gaining mass. When gas funnels into the galactic center, it forms an accretion disk around the black hole. Friction within the disk heats the gas to extraordinary temperatures, causing it to glow brightly. In some early galaxies, central black holes may have shone as quasars, outshining all the stars in their host galaxy combined. These quasars were not permanent. They flickered on and off depending on the availability of infalling gas. But their influence was significant. Radiation from quasars could heat surrounding gas, regulating further star formation. This feedback loop, star formation fueling black hole growth, black hole radiation regulating star formation, established a dynamic equilibrium that still exists today. Galaxies and black holes evolved together, each shaping the other. The universe does not build systems in isolation. It builds networks of interaction. Clusters of galaxies began forming where dark matter filaments intersected most strongly. At these intersections, mass density was highest. Over time, dozens or hundreds of galaxies became bound together in clusters. Within clusters, galaxies orbited a common center of mass dominated by dark matter. Hot gas filled the space between galaxies, glowing faintly in X-rays. Dark matter halos merged into even larger structures. Clusters became the largest gravitationally bound systems in the universe. Even larger than clusters are superclusters, immense groupings of clusters stretching across hundreds of millions of light years. Yet even these enormous formations are separated by vast cosmic voids. The cosmic web became fully articulated. Filaments like threads, nodes like intersections, voids like enormous empty chambers between them. And throughout this vast architecture, dark matter remained the dominant mass component. Stars provided illumination. Dark matter provided structure. As the first billion years passed, the universe matured significantly. Star formation reached peak rates a few billion years later. Galaxies grew brighter. Elements became abundant. Planetary systems began forming more frequently. But the memory of the early silent age was embedded in every structure. Even today, astronomers observe dwarf galaxies that may resemble early proto-galaxies. These small systems provide clues about how larger galaxies assembled. Some dwarf galaxies have very low metal content, indicating they formed from relatively unprocessed gas. Studying them helped reconstruct early cosmic evolution. Black hole growth in the early universe remains one of the most intriguing puzzles. Some quasars observed less than a billion years after the Big Bang host black holes billions of times more massive than the Sun. Growing a black hole that large in such a short time requires rapid and sustained accretion. This implies that early environments were dense and dynamic. Galactic mergers likely funneled large amounts of gas towards central regions, accelerating black hole growth. The early universe was therefore a time of rapid transformation. Yet even then, the broader cosmos remained calm. Expansion continued steadily. Voids expanded. Gravity pulled within dense regions. Across vast scales, evolution remained gradual. There were no sudden universal upheavals. Only local events embedded within larger stability. As galaxies matured, their star formation rates eventually slowed. Gas reservoirs were consumed or heated. Some galaxies evolved into elliptical forms after repeated mergers. others maintained disk structures. Diversity emerged. From simple beginnings, complex patterns arose. What began as nearly uniform gas evolved into billions of distinct galaxies, each one tracing back to dark matter halos forming in the cosmic dark. The first black holes continued merging through galaxy collisions. When two galaxies merge, their central black holes eventually spiral toward each other. Over millions of years, they approach, emitting gravitational waves. Finally, they coalesce into a single larger black hole. This process builds ever more massive central black holes in large galaxies. And yet, despite these dramatic interactions, the universe remains remarkably stable overall. No galaxy collision instantly destroys structure. Stars rarely collide directly because of immense distances between them. Galactic mergers unfold over immense timescales. Even chaos operates gently on cosmic scales. The birth of galaxies and black holes did not eliminate darkness from the universe. Darkness remains dominant. The difference is that luminous systems now float within it. Vast emptiness still stretches between clusters. The ratio of dark to light remains overwhelming. But within that darkness, structure now thrives. The Silent Age ended not with sudden brightness, but with gradual illumination spreading across the cosmic web. Each generation of stars enriched the universe further. Each merger deepened gravitational wells. Each black hole grew slightly larger. Over billions of years, the universe assembled the framework we inhabit today. Our own Milky Way contains relics of early mergers. Streams of stars wrap around it, remnants of smaller galaxies absorbed long ago. At its center lies a supermassive black hole, Sagittarius A star, weighing millions of solar masses. That black hole may trace its ancestry to the first generation of stellar collapses. Thus the early silent cosmos echoes within our present galaxy. The hydrogen clouds of the Dark Ages became proto-galaxies. Proto-galaxies became mature galaxies. Mature galaxies became systems capable of forming planetary environments. Planets formed. Chemistry diversified. Life emerged at least once. All seeded by gravity acting quietly in darkness. The story of cosmic evolution is not one of sudden transformation. It is a story of accumulation, of merging, of gradual amplification. The first stars were the opening spark. The first galaxies were the first architecture. The first black holes were gravity reaching deeper intensity. And from those beginnings came everything else. As you imagine the early universe transitioning from darkness to structured light, picture countless proto-galaxies assembling like faint lanterns in the void. Picture black holes forming quietly at their centers. Picture filaments stretching like invisible bridges between them. Picture expansion widening the spaces between clusters. The universe grows not through haste, but through persistence. Gravity acts continuously. Expansion proceeds steadily. Time advances silently. The Silent Age gave birth to the Age of Galaxies. And the Age of Galaxies paved the way for the Age of Planetary Systems. Tonight, the sky above you is filled with distant echoes of those first structures. Some of the stars you see are billions of years old. Some galaxies visible through telescopes are shining as they were when the universe was young. All of it traces back to dark matter clumping quietly in primordial darkness. The first stars ignited alone. The first galaxies assembled irregularly. The first black holes formed silently. From that beginning, cosmic complexity unfolded. Not in a rush. Not in chaos. But in patient stages. And that patient unfolding continues even now. Galaxies still merge. Black holes still grow. Star formation still occurs. Expansion still carries structures apart. The cosmic story moves forward. But its foundation remains that Silent Age. The era before galaxies existed. The epoch when gravity prepared the stage. Where darkness held potential. Where hydrogen waited. And where, slowly, the universe learned how to shine. From that deep silence emerged structure. From structure emerged light. From light emerged worlds. And from those worlds emerged observers capable of reflecting on the beginning. The early universe was not empty. It was becoming. And in its becoming, it set into motion everything that followed. A cosmos born in brilliance. Temporarily dark. Then gently illuminated by the first stars. And forever shaped